Okay, so now we go to the first example. We are having a DC level in white Gaussian noise with unknown amplitude. But as we said, anything anything that is informed to you is information. The information is not sometimes, the concept of information is kind of abstract. Uh, Everything you know may it be very specific or may it be very abstract or it's even just a small hint. It's information. Okay, so um, so sometimes you will encounter minor informations, and yet the minor information gives you a very important implications for the problem. So here we have DC label in white Gaussian noise. Now you have a lot of information. You see that? The first thing is it's a DC label. So it's not like a sinusoidal. It's not like a Gaussian random process. No, it's a DC label. So we have a here, a constant, a, and then it's in WGN. Okay, as we mentioned before, white Gaussian noise is something simple and easy to deal with. Well, in fact, if you do not have white Gaussian, you have color noise, then it gives you a lot of trouble, as we see before, right? In previous chapter, we deal with the color noise, where we have correlations, right? Um, then the other thing is it gives you information about a larger than zero. Uh, do not ignore this minor information. It's very important. Okay, so we have a DC label in WGN detection problem. So the H0 is Xn equal to noise only, or it's a H1 uh, which has signal equal to A plus Wn, and then again it's taken multiple samples. It's taken multiple samples. It goes from uh, 0, 1 all the way to n minus 1. Okay, so uh, the value of A is unknown. Although a priori, the concept is very important. A priori, we know that A is larger than 0 and Wn is Wgn with variance sigma square. Again, this is the important information. Otherwise, if you think about it, without this and this, we will not be able to write out its probability density function. Then likelihood ratio wouldn't be available, right? So do not ignore any information, even if it looks minor at the beginning, it will play out later on in the formulations. So the NP test is to decide H1 if this likelihood ratio is larger than gamma. And then how do we write down the likelihood ratio? We will write P of X condition on A H1 parenthesis, and then this 1 over 2 pi sigma square n over 2 exp, and then this is the Gaussian, right? This is the multivariate Gaussian. We call multivariate Gaussian for this. And then this thing is just zero mean Gaussian. So it's multivariate zero mean Gaussian for this here. It comes from here. Okay. Then we write the likelihood ratio out. Then uh, go to the next page, 192. We take the log and simplify it. We will have something like this. Then it will, of course, you take the log at the left hand side. You need to take the log at the right hand side. So, or this is larger than log, then, or this is larger than This is what? This is just reformulation, okay? From here to here, reformulation. How come? Uh, the issue is we're trying to put samples at one side and parameters at the other side. That's what we're trying to do. So as you see, you just multiply it in, and then you put this term at the right hand side, then you get this term at the right hand side, and then also you have this. Of course, you want to sort of divide this a out so that you kind of have this summation of xn at the left hand side, right? So uh, now here the a larger than 0 property is critical here, because if you want to divide a, you need to know the plus or minus sign of a, right? Because if it's a minus sign, when you divide it, it becomes smaller than, right? But here, since we know a priori a is larger than 0, then we divide a, it doesn't change the sign. So this larger than is still larger than. So we have this larger than, larger than, this sign of larger than here. And then you divide this whole thing by a, and then a disappear. And then the right hand side, you have everything being divided by a. Finally, we scale by 1 over n. This is sort of like we want to just like a normalization factor. Okay, it doesn't matter. Since we know n is a constant, so it doesn't matter. We just divide it by n. So 1 over n, and then divide it. It looks more like a sample mean. Recall that sample mean, right? We take samples, we take the mean. So it divide by n, then n at the right hand side. Then we rename denote this whole thing as gamma prime. Now we have a test which tells us that you do this t of x, which is the summation of the sample divided by n, and you compare with the threshold. Okay, then the key question is whether we can implement this detector without knowledge of the exact value of a. Clearly, the test statistic, which is the sample mean of the data, does not depend on a, but it appears that the threshold gamma prime depends on a. So this dependence is only illusory, as we will demonstrate. Recall from chapter 3 that under H0, T of x, which is the sample mean, is distributed by Gaussian distribution, except its variance is sigma square over n instead of just sigma square. It has to be divided by n. Hence, our PFA is T of x larger than gamma prime. This is where we decide H1, right? This is where we decide H1. And then condition on H0, we decide H1. This is a false alarm. So this is sort of the PFA. Then it's a Q function of this gamma prime over square root of sigma square over n. And then, of course, the gamma prime, you take the inverse function, you put this at the out, put this at the left hand side, then you get your gamma prime equal to this, which is independent of a. So now, if I'm asking you to say, I want to have a detector that has a detection performance PFA equal to 10 to the minus 2, then you can give me a gamma double prime. You can give me a gamma prime, right? You have no problem with that, because you can just take the inverse of the Q function and divide it by those things, and those things are shown known, right? So the PDF of T under H0 does not depend on A. The threshold which is chosen to maintain the constant PFA, can be found and will not depend on A. So, since the test is actually the NP detector, Neyman Pearson, remember the spirit of NP detector is that you constrain your PFA to a threshold and then you maximize your PD. Okay, so it's optimal that it yields the highest PD for given PFA. But however, the PD will depend on the value of A. So more specifically, if you calculate the PD is equal to PR, T of X larger than gamma prime condition on H1, because this is where you decide H1, right? Condition on H1, you decide H1, that's PD. Okay, so now you have a H1. On the H1, your T of X, which is X bar, is distributed by Gaussian distribution of A and then sigma square over N, so that your PD will be your gamma prime minus A divided by this Q function, which is sort of a shifted Gaussian distribution. We call this, you have mean equal to A, so that your PD will need to be shifted by A and take the Q function, which is the tail, right? The tail probability. So your PD will be a Q function of this thing. And then Q function of this thing is, you can do a little bit of transformation. You put this gamma prime, replace that gamma prime by this. You have your gamma prime as a function of PFA. You put that in here. So you have a PD as a function of PFA and without gamma prime. So as expected, PD increases with increasing A, right? If you increase A, then it's a minus sign in the Q function. As a result, your PD increases. So this is illustrated in figure. So we'll take a look at that later. So we may say that over all possible detectors that have a given PFA, the one that decides H1 if this is all possible detectors that have a given PFA, for example, 10 to the minus 2 as an example. The one that decides H1 if this is larger than that, then that gives you the highest PD. Although the PD is still dependent on A. We don't know the exact value of it, but this will give you the highest PD. So let's take a look at this. On the H0, it's very simple, right? On the H0, we go back to see it one more time. On the H0, it's only a zero mean Gaussian. On the H1, it's an unknown BC label with a Gaussian. Okay, so on the H0, it's a PDF. It's a PDF uh, of zero mean Gaussian. Then you have H0, you have X bar, and then of course this is your test statistic, which is the X bar. And then the test statistic gives you this PDF. And then you set a threshold gamma prime, you're going to have a PFA, right? But if you look at the second figure, it's more clear here. With whatever A, the PDF of H0 does not change, right? Uh, how come it does not change? Because it's not dependent on A. H0 is not dependent on A. But if for H1, then it will be a different story. Because A is 0.5, then the mean will be 0.5, right? If A is 2, then it will be shifted to here. As a result, on the H1, the PDF will shift a little bit depending on the value of A, depending on the value of A. But the PDF of H0 is unchanged. As a result, let's say you set a threshold here. Your PFA is fixed. Then if your A is 0.5, then this is your PD for A 0.5, right? Because this is a distribution of the H1, and then it's when it's larger than you say H1, so this is the PD. But if the A is larger, for example, it's 2, you set the same threshold. Notice that you set the same threshold. The threshold is not changed, but your PD goes from this small area to a large area. So your PD does dependent on A. So that's the reason. That's kind of the reason. Okay. So the the rationale of this is to say that uh, as long as A is larger than 0, this argument sustains. That's why we say this is the most powerful detector, because no matter what value of A is, you always get the best PD. So this type of test, when it uh, exists, it's called uniformly most powerful test. It's uniformly most powerful. In other words, for whatever A, it's always the most powerful. But in some other cases, it may be hard to find most powerful, uniform most powerful. It's really different from case to case. In some cases you find it, in some cases you don't. Okay. Um, so let's take another example. Let's take a look at the Bayesian approach. The Bayesian approach here. The Bayesian approach assigns prior PDF to theta 0 and theta 1. As we assumed before, when we set some parameter as random variables and we have some prior knowledge about it, then we will use the name Bayesian. Even in chapter 3, chapter 4, we use this name Bayesian, right? So if we have a prior PDF to theta 0 and theta 1, we will call it a Bayesian. But remember previously, in previous example, we do not have this prior PDF. So in doing so, it models the unknown parameter as realizations of a vector random variable. If the prior PDFs are denoted by P of theta 0 and P of theta 1, the PDF of the data are, this is Bayes rule, right? We call Bayes rule. When you have x dependent on theta 0 and h1, you can actually integrate it out by Bayes rule. So this is p of x condition on h0 equal to integration of p of x dependent on theta 0. This is our initial setting, right? Our initial setting is condition on h0, you have theta 0, condition on h1, you have theta 1. But since you have prior knowledge, you try to integrate it out. So you have p of theta 0, you b 0. As a result, you have this and this, where this is the conditional PDF of x conditional theta I, assuming hi is true. The unconditional PDF, unconditioned means that it unconditioned on theta, but it's still conditioned on h. So p of x h0 and p of x h1 are now completely specified because you have this integration, and this is by Bayes rule is assumed to be known. Okay, so then with the Bayesian approach, the optimal NP detector decides h1 by, again, this is the likelihood ratio, p of x condition on h1 p of x conditional h0 equal to this, and then we do the integration on that. So you have this p of x theta 1 h1 p of theta 1, and then b theta 1, then here is with respect to h0. Then the required integration are usually not that easy because it's multidimensional. Sometimes this theta, let's say that you have 3 variables with it, or you have 5 variables with it. So sometimes the integration will be a little bit difficult. But uh, after all, we have come up with a formulation at least. Other than just nothing, at least we have something, right? We have this uh, formulation so that we can go with the formulation and do the integration. Okay, so uh, assume that for the DC level in white Gaussian noise, here is a more general rule, but now we have a specific example. Assume that for DC level in WGN, A is unknown and can take on values from minus infinity to plus infinity. We assign the prior PDF as Gaussian. Okay, so this is kind of like a, a simple way of doing it. Uh, in other words, we are just make a simple assumption by saying that A is a Gaussian distribution with zero meaning sigma A squared. So A is independent of W usually. I know that uh, sigma A squared, when it approaches infinity, the PDF becomes a non-informative prior. So the conditional PDF under H1 is assumed to be, this is a multivariate Gaussian with A being a variable, right? A being the mean of the Gaussian distribution. Under H0, PDF is completely known. So this is completely known. So according to Bayes rule, this is basically Bayes rule. Theta 1 is equal to A. The NP detector decides H1 if P of X conditional H1 over P of X conditional H0 is equal to this. And this is integration minus infinity to plus infinity. Because of what? Because we are doing integration on the parameter A. But A is not a parameter. A is a random variable here because we have assumptions on its probability density function. So we integrate it out. And it's a Gaussian, so it has to go from minus infinity to plus infinity and larger than gamma. Okay, so uh, then we start to do the integration of this thing. We just pull this in. This is like this, and this is a Gaussian, so it's a Gaussian, right? This is a Gaussian, so this is this. This is this, and this is this. So we try to integrate with respect to A from minus infinity to plus infinity. And then Q of A, it's just a, a reformulation. There is some confusion about, a little bit of confusion about, I think, the Q function. The Q function here is not the Q function before. It's just a little bit abuse of the notation, but you know what it is. We are assuming Q of A as this. Then we have, upon completing the square in A, we try to reformulate this Q of A, write it out, and simplify it, and eventually we come up with something like this. We come up with something like this. Okay, so that we take some parts out, then we do some simplification, and eventually we get this P of X conditional H1 over P of X conditional H0 equal to something like this. Then we come up with something like this. And as long as it's larger than gamma, then we will decide H1. So take logarithms of both sides and retaining only the data dependent. We will get X squared. larger than gamma prime. Or even more simpler, we will say x bar, absolute value of x bar larger than square root of gamma prime. So this is similar to the detector we proposed in the previous section. So in order to set a threshold, we do not need to know the knowledge of sigma a squared. But if we had assumed A is distributed by this, then we would need to know mu A and sigma A squared to implement the Bayesian detector. Then of course the performance is also one thing we can do, and it will be in the later chapter. And if we use the generalized likelihood ratio, in this case we have theta 1 equal to A, and there are no unknown parameters on the H0. The hypothesis test becomes H0 is A equal to 0, or H1 is A is not 0. So the GLRT will decide H1 if this is larger than gamma. But the MLE is found by maximizing this whole thing, the whole thing. But this has not been taught. Like I say, this is an estimation of a continuous variable, which will be taught in the later chapter. In fact, it's in the Stephen Case textbook, volume 1. Right? We have not speak about it yet, but by maximizing this, you get your A hat equal to X bar. That's the maximum likelihood estimator. Then you put it in. So the likelihood ratio test will be this is this, and this uh, this thing needs to have a mean A here. Recall what we did before. We have a X bar. We have an A here. Now A is replaced by A hat, which is X bar. So we now have this formulation. Of course, then we do some simplifications. Eventually, it comes down to this form. And then we will decide H1 if this is larger than gamma prime. But it's a coincidence. It happens to be the same as this one. Okay. So I think we have go from deterministic, to random process, which is chapter 5, and then come to this stage, which has unknown parameters, and the unknown parameters can be parameters or can be random variables, depending on what information you have. So I think we just cover this part of the chapter, and we will give some practice questions later on. Okay, so we will stop for a moment and then come back.